Okay, so today we're going to start calculating truss forces. So the forces acting upon our members inside of our trusses, we want not just to know what it does, but actually how much force can be applied, since we can go and look at modulus elasticity and moment of inertia and figure out what type of material we want to use. So we're going to look at our forces. There's two different types that we're going to look at. There's compression and tension. Compression is when the joint is being squeezed. So the two members going into it are squeezing and pulling that together. Well, tension is going to pull outside or away from a joint itself. So an individual member can either be a compression member or it can be a tension member. So the truss is, here's the right side and the left side of the truss that's there. There's the gussets that are sitting on the inside and everything that's welded together. But what we're going to look at is then calculating those trusses. So we've got a simple truss. Simple truss is triangles, so it retains its shape when a force is applied. So if you take this shape right here and you throw it, you can see how it's moving, and it could change its shape. But if you take this shape and throw it or shake it, you're still going to have that same basic shape and structure. So each one of those trusses is held together and supported by rollers and pins. The pin itself is often denoted with a triangle. When you're using a pin support, you've got two different dimensions or directions of your forces. You can have them in the Y direction and the X direction. Then with that roller, it can support a structure in only one, because something's resting upon it, but it can still rotate or move left and right, but it can't go up and down any longer. Pin, it's pinned in there. You got to fight and back down and then up and left and then right with that structure itself. So both of those are being used to help show it. We've got models of actual bridges we can look at later in class. So when we gotta solve a truss, a couple different things. We don't need to be a lawyer right now. We're starting at the basics. Basic things you're going to just work with when we're solving these trusses right now. All members are straight. All loads are being applied to the joints. All joints are pinned and frictionless. Each member has no weight, and members can experience tension or compression forces. Again, we know all these aren't true, but once you become a structural engineer, you can go more advanced. We've got to start at the kindergarten level for these. So once we go through and we take all those assumptions in when we're trying to solve for things right now, first thing we've got to do is look and see if a truss is actually statistically determinate. That means that mathematically 2 times the number of joints equals the number of members plus the number of reactions. So mathematically proven. If you want to look up where it comes from and all the math behind it, feel free to do so. But right now we're just going with that. 2 times J equals M plus R. So they give us this example truss right here. It has 4 joints, A, B, C, and D. It has 5 members, 1, 2, 3, 4, and 5. And it has 4 reaction forces because we have a pin, which is 2. So what do we have? We have 2 times 4, number of joints, does not equal the 5 members plus the 4, so that is not statically indeterminate. So therefore it wouldn't be in balance, so we couldn't do a calculation. So how do we change that? Well, we changed one of the pins to rollers. We still got 4 joints, 1, 2, 3, 4. We have 5 members, 1, 2, 3, 4, 5, but now we have 3 reaction forces, 2 at the pin, 1 at the roller. We've got that we could solve for. Real life example, this bridge in Brooklyn, it's got 19 joints. They're represented by the red dots, 35 members connecting those joints, 3 reaction forces with a roller, and then a pin. So therefore 38 equals 38. That is a good working bridge. So once we got that and we know we can go forward and the bridge is going to work, we do some calculations, we've got to look at equilibrium. We don't want the bridge to move. So first thing we want to look at when we're solving these trusses is the moments. We've talked about them in previous lessons. We're going to talk about them now. The sum of the moments needs to be equal to 0. So the moment at every single joint needs to counter with the other ones and have it equal to 0. Also true that we've talked about before. The sum of all the forces in the x directions needs to equal 0. So we've been looking at it before, we've talked about it, now we're going to bring it into our larger trusses and our larger problems. Same thing, sum of all the forces in the y direction needs to be equal to 0, so at every individual joint that we look at, we've got to make sure the sum of all the forces in the y direction equals 0. So with that, we've come up and we've got the calculation here. We will go through and we'll solve this one in class. I'm going to start things off and we'll give you different things and different notes to go through, but feel free to flip through the rest of the notes and follow along with here. They'll go step by step, but again, we will go over most of this in class instead of following along with these here.